Hello and welcome to today's class. Today we're going to be looking at some basic concepts when we're talking about fluids. We're going to be talking about what a fluid is. We'll look at some basic definitions. We'll talk about volume, pressure, density. We'll talk about hydrostatic pressure, what we mean by internal flow, external flow, different sorts of flow patterns, so one-dimensional, two-dimensional and three-dimensional. We'll then move on, and when we're talking about flow patterns, we'll talk about steady and uniform flow, steady and non-uniform flow, non-steady and uniform flow, and then finally non-steady, non-uniform flow. We'll then move on and we'll have a look at conservation of mass, forces, and fluid flow, resistance to that fluid flow, so inertial forces and viscous forces. And then that would bring us to talk about the coefficient of viscosity. And finally, that brings us on to Reynolds number. These are all concepts that you've probably come across before, and concepts that we're going to be using, terms that we're going to be using moving forward in this module. So the first question we need to ask ourselves is, when we're talking about fluids, what is a fluid? Now, if we think about different phases of material, we've got solids, fluids. Now, fluids are actually made up of liquids, vapors, and gases. Okay, so a solid material can resist deformation to an applied force. So if we had a solid and we were to apply a shearing force, so let's say we're going to apply a force in this direction. Now, deformed shape, we were shearing that. That deformed shape would look something like this. So when we talk about materials, mechanics of materials type stuff, we talk about shearing forces, shearing stresses, and so on. However, when we're talking about fluids, our fluids do not resist that shear. Our fluids will deform continuously under that shearing force, i.e. it will flow. So when we're talking about fluids, we can't shear our fluids. They will flow. Okay. When we talk about the different sorts of fluids, our liquids, approximately constant volume, our vapors, our gases will fill the space available to them. At a molecular level, when we're talking about solids, there's very little movement in the molecules relative to each other. When we're talking about liquids, the molecules are attracted to each other and there's constant spacing, i.e. we have a constant volume. However, the molecules can move easily relative to each other, i.e. we see this flowing. When we're talking about vapors or gases, there's very little force between those atoms and those molecules. It's a fairly random motion. The space between the molecules is determined by the space available, i.e. the volume, the vapors and the gases will fill that space that's available to them. However, when we're talking about fluids in this module, we're going to be talking about them as a continuum. That is to say, we're not going to account for the individual molecules. We're going to consider fluid as a continuous material. It's the average of many different molecules. So when we're talking about fluids, we need some basic definitions. So let's go through some of those. Okay, so the first thing we need to think about are when we're talking about volumes. So volume, generally we give that a capital V. Okay, however, we may, when we're talking about fluids, rather than talking about volume, talk about specific volume. Okay, so V equals volume. And specific volume is simply the volume divided by the mass. Okay, notice the subtle difference there. Volume is uppercase V, specific volume lowercase v, and often you'll see it with this dot above it. Okay, so to get from volume to specific volume, we simply divide through by the mass. Okay, now specific volume, volume divided by mass. Now notice that actually is just the inverse of density. Okay, so we're used to saying density equals mass over volume. So therefore volume over mass must simply be the inverse of density. Okay, so specific volume, volume over mass, specific the inverse of density. So in order to get specific volume, simply take the volume and divide it by the mass. We also, so that's specific volume. We also need to think about the term specific weight. Weight is another term that we will come across. Okay, so W you can think of as our weight. And again, subtle difference, lowercase w with that dots above it, specific weight. Okay, so in order to get from volume to specific volume, we simply divide by the mass. However, this time we're going to divide through by weight. Sorry, by volume. So our specific weight is simply our weight, uppercase, weight divided by volume. Okay, now our specific weight, our weight is our mass times by our gravity, and our volume, we times that by the inverse of the volume. Now, inverse of volume, we know density equals mass over volume, so therefore volume must be mass over density. So inverse of volume is simply going to be density divided by mass. So mg times by density divided by mass. Clearly, that mass and that mass are going to cancel out. So what are we left with? Our specific weight is simply our density times by our gravity. Okay, so to get specific volume, we take volume and divide by mass. To get specific weight, we take weight and we divide through by volume. Okay, so specific volume, specific weight. We will also use specific gravity. Now, specific gravity is simply the gravity or the density of something relative to water. Okay, so specific gravity, simply the density divided by the density of water. Okay, now the density of water, pure water, is 1,000 kilograms per meter cubed. So if we're talking about the specific gravity, so something is the gravity relative to water. So the specific gravity of water is 1. It's 1,000 divided by 1,000. If we talk about the specific gravity of mercury, for example, it is 13,560. That's the density of mercury, kilograms per meter cubed, divided by the density of water, which is 1,000 kilograms per meter cubed. So therefore, the specific gravity of mercury would be 13.56. Okay, the specific gravity of mercury. So we talk about specific volume, we talk about specific weight, we talk about specific gravity. We also will use pressure. Pressure is simply force per unit area. It's actually the same as stress, force over area. Pressure is also force over area. When we talk about pressure, we will talk about gauge pressure and absolute pressure. Now, gauge pressure is simply the pressure of something measured with reference to the air pressure in the surrounding atmosphere, whereas absolute pressure is simply the pressure measured relative to a perfect vacuum. So therefore, now absolute pressure equals our gauge pressure plus pressure of our local atmosphere. Okay, so when we're measuring the pressure of something, we need to define what we're measuring it relative to. Are we measuring it relative to the local atmosphere, or are we measuring it relative to a vacuum? When we talk about standard atmospheric pressure, a standard atmospheric pressure, 1.013 times 10 to the 5 pascals. Okay, so normally standard atmospheric pressure 1.013 times 10 to the 5 pascals. That's actually also known as normal pressure. That is the normal pressure, and it is 1 atmosphere, which is approximately 1 bar. 1 bar is 1 times 10 to the 5 pascals. Okay, so that is our standard atmospheric pressure. And 1 times 10 to the 5 pascals would be 1 bar. Now, standard temperature would be 273.16 degrees Kelvin or 0 degrees Celsius. So our standard temperature is freezing, 0 degrees Celsius. Our normal temperature is actually 298 degrees Kelvin or 25 degrees Celsius. Okay, so standard temperature and normal temperature. So our standard atmospheric pressure, same as our normal pressure, 1 atmosphere, 1 times 10 to the 1.013 times 10 to the 5 pascals. It's basically 1 bar. But we also come across, well, often when we're measuring pressure, we'll talk about PSI, pounds per square inch, particularly if we're dealing with units, imperial units. 1 pascal is approximately, if we're talking about SI units, 6.8 times 10 to the 5 pascals. Okay, so we can relate when we're pumping something up, a tire or something like that, and we're talking about the gauge pressure, we can relate to 1 psi to approximately 6.8 times 10 to the 5 pascals. Other terms that we'll use, we need to think about, we can often think of gas as an ideal gas, i.e. it will obey PV equals RT, where R is our specific gas constant for air, and for air that is R is 287 joules per kilogram degree Kelvin. Okay, so when we're dealing with fluids, we will generally talk about fluid statics or fluid dynamics. When we're talking about static fluids, quite often we'll talk about hydrostatic pressure. What do we mean by that? Hydrostatic pressure. Okay, so let's consider a column of fluid here. It's sat in equilibrium, so therefore the upwards forces are equal to the downwards forces. Clockwise moments are equal to the anti-clockwise moments. We've got atmospheric pressure acting on the top surface and on the bottom surface. On this bottom surface down here, we would have some pressure. Let's call that P. This column of fluid is of height H, and its area let's call that A. Its density is D. Okay, so if this is setting it up in equilibrium, we know that our force up so the force on this bottom surface, force on the bottom surface is the same as the weight of the fluid acting downwards and the force exerted from this local atmospheric pressure. So the force up equals the weight of the fluid plus the force from atmosphere. So our force up, well, it's going to be forces pressure times by area. We know that pressure equals force over area. So therefore, force equals pressure times by area. So if we're talking about the force up, it's going to be this pressure. Pressure. That's going to be the absolute pressure because we've got the atmospheric pressure acting on there as well. So atmospheric pressure times by the area. The area is delta A. Delta A equals the weight of the fluid. The weight of the fluid is going to be the volume of the fluid times by density times by gravity. So the volume of the fluid is going to be delta A times by H. Delta A is our cross-sectional area, H is our height, so that's going to be the volume of the fluid times by density, to turn that into mass, times that by gravity, to turn that into weight. Plus the force from atmosphere, again, just like on the bottom, it's the pressure times by the area is going to be, the area is delta A, the pressure is the local atmospheric pressure acting on top of the surface there. Okay, now notice all of those terms have got delta A in, so we can cross those through. We can cancel those. We can divide through by delta A. So our absolute pressure on the bottom surface equals H rho G. Generally, you'll see that as rho GH plus the atmospheric pressure, local atmospheric pressure sat on top of the surface there. Or if we want the gauge pressure, we simply subtract the local atmospheric pressure. So we'll end up with rho GH. Okay, so when people talk about hydrostatic pressure, generally they'll just use that. Now we're talking about gauge pressure. Hydrostatic pressure is simply rho GH. It's the amount of fluid sat on top of your surface. Now, when we're talking about fluid flow, we can either talk about the fluid moving relative to an object or the object moving relative to the fluid. We can also talk about pressure and velocity varying with time and space. So if we're talking about compressible flow, the density is a function of pressure. If we're talking about incompressible flow, the density is constant. Now, clearly for most calculations, incompressible flow massively simplifies things. If we can assume that the density is constant, then a lot of our calculations are massively simplified. If we're talking about fluids which are moving very slowly, then generally we would assume incompressible flow. As soon as we start talking about fluids moving very fast, then we need to think about compressible flow, certainly when we're talking about transonic, supersonic flow, and so on. And we'll come on to those terms. But when we're talking about something moving very fast, the flow is compressible. So if we're talking about incompressible flow, and we're talking about fluid flowing through an object, there's certain terms which we can consider. Let's consider a pipe, which our fluid is flowing through. So if I draw out a pipe like this, this has a cross-sectional area. Let's call that A. If we consider a cross-section, got another cross-section here. Our fluid is moving through this pipe. So there's our fluid moving through our pipe, and let's give that a speed u. Okay, so pressure, let's call that P. Velocity, u. Area, A. Density, rho. Okay, so the mass of fluid moving through our pipe, we will often refer to the mass flow rate or the mass flux. Okay, so the mass flow rate or mass flux is simply the mass of the fluid moving past a certain point. Okay, so mass flow rate, given that symbol there, equals rho u a. Okay, it's simply the density times by the velocity times by the area, and the units would be kilograms per second. It's the amount of mass moving past a certain point at a certain amount of time. So that's our mass flow rate. We'd also need to consider, we also talk about our volumetric flow rate. Flow rate, volumetric flow rate is U times by A. Okay, it's the volume of fluid moving past a point in a certain amount of time, U times by A, which is our mass flow rate divided by our density, and that's meters cubed per second. So our mass flow rate describes the mass of fluid passing a point in a certain time, and our volumetric flow rate talks about a volume of fluid passing a point within a certain amount of time. Okay, so when we're discussing fluid flow, we can talk about external flow or internal flow. We've talked about internal flow through a pipe. We can potentially have fluid, however, flowing over an object we consider I were to draw an aircraft, which might look something like this. So I've got my aircraft and our fluid traveling relative to my aircraft. Let's say it's traveling with a velocity u. Okay, so we can have external flow past an aircraft like that, for example. Or alternatively, we could have a flow through a pipe. So we might have a stream tube, and inside that tube, we can draw our stream lines. So our stream lines show the fluid flowing through that tube. Okay, and stream lines are used to represent the direction or flow, the direction of the flow. So fluid flow cannot flow across a streamline. Fluid doesn't flow across a streamline. It can only flow along a streamline. So those lines, those streamlines there are representing the fluid flow. If we've got a stream tube, our stream lines are nice and parallel to the edges of that tube. However, if we've got an object where, let's say we've got a backward facing step, so let's say we've got a tube which looks something like this, and our streamlines in there. So our fluid might flow something like this. Now, our fluid is flowing along our pipe, and our pipe expands, our fluid expands. So here we've got a high pressure region where our streamlines are close together. Here we've got a low pressure region, lower pressure region where our streamlines are further apart. And what we actually get is our streamlines spread out. In the corners here, we'd actually see recirculation. We'd actually see our fluid going around here, looking something like that. So we often use streamlines to represent or to show the flow of the fluid through an object. What we can also do is use vectors to show, to represent the velocity of a fluid. So if we were to consider a wall, for example, let's say we've got a wall here, we've got some fluid flowing above this wall here. So our free stream velocity, our velocity away from the wall, let's call that u. As that approaches that wall, that's going to get smaller and smaller. And actually u equals 0 on the wall, because we're trying to shear our fluid. As our fluid is shearing, as our molecules are rubbing over top of each other, u equals 0 at the wall, because our molecules are touching the wall and the wall is stationary, so therefore the molecules must be stationary. So u equals 0 at the wall, u, sometimes we refer to this as u infinity, so u, a infinite distance away from the wall, our free stream velocity. Okay, and you can see we're using vectors there to represent the velocity of the fluid flow. 0 at the wall, free stream velocity away from the wall. So we can have different sorts of flow patterns, 1-dimensional, 2-dimensional, or 3-dimensional. If we consider a pipe, let's say our pipe looks something like this. Got fluid flowing through our pipe. It starts off in this section here, a certain velocity. As our pipe contracts due to conservation of mass, our velocity is going to increase, so therefore I'll lengthen those vectors. Okay, so we're showing that the velocity is increasing there. Okay, so this is one-dimensional flow, 1D flow. Now, u equals a function of x. Okay, clearly, if x is our origin, we say x is here, going in this direction. U is a function of x. As x changes, u changes. Okay, so that's 1D flow. Now, 2D flow, u equals a function of x and y. Okay, so if we were to consider a wall and our free stream velocity, let's say it's u1 here, it increases in speed here, u2. Okay, so clearly the velocity is changing. Same coordinate system. U is clearly a function of x. Okay, but because it's next to a wall, u is also, this is our y direction. If we assume y is vertical, u is also a function of y. Okay, so as we get closer to the wall, so that we were discussing a minute ago, it's approaching 0. U is approaching 0, so U is going to get much smaller at the wall. Okay, due to those shearing forces inside our fluid. Okay, so we can clearly see U is a function of x, U is also a function of y. Okay, so it's two-dimensional flow. Okay, and we will also get three-dimensional flow where U is a function of x, y, and z. Okay, I'm not going to attempt to draw that, but if you imagine the z coordinate coming out of the page, or z axis coming out of the page, U not only changes in x and y, but it also changes in z. Okay, we can have three-dimensional flow. So when we're considering different flow patterns, what we're actually talking about there is the change of the flow relative to space. And we were talking about on the previous slide, flow patterns 1D, 2D or 3D. So one-dimensional space, two-dimensional space or three-dimensional space if that velocity changes relative to that space. We also need to think about fluid flow and how that changes with respect to time. Okay, and that gives us a couple of definitions. Okay, so steady flow, note, is going to have no variation with respect to time. With respect to time. Now, uniform flow has no variation with respect to space. Okay, so we can therefore have four different sorts of flow. We can have steady uniform flow, steady non-uniform flow, non-steady uniform flow, and non-steady non-uniform flow. Okay, so let's consider each of those. So if we consider first of all steady and uniform flow, so it's steady and uniform. So it's steady, therefore there's no variation with respect to time, and it's uniform, therefore we've got no variation with respect to space. So if we were to show an example of that, let's consider a pipe. We're talking about fluid flowing through that pipe. Position 1 here. Let's call that position 1. Let's consider position 2. Okay, so at time 0, it looks like this. At time after 1 second or 2 seconds or whatever, it would look exactly the same. The fluid is not changing with respect to time. It's also not changing with respect to space. Okay, the velocity at 1 is exactly the same as the velocity at 2. Okay, so it's not changing with respect to time or space, therefore it's steady and it's uniform. Okay, the next example would be steady non-uniform flow. So steady and non-uniform flow. An example of that would be if you've got a tapered pipe, our fluid starts in this position, that is certain velocity. Let's call that position 1. Down here, due to conservation of mass, the same amount of fluid passed in the same amount of time is going to have to increase in speed. Let's call that position 2. Okay, it's steady, so at time 0 or at time 1, it looks exactly the same. It's not changing with respect to time. However, it is changing with respect to space. Okay, the velocity at 1 is clearly less than the velocity at 2. Okay, so u is a function of space. Okay, so we've got steady uniform flow, steady non-uniform flow, and then harder to draw. But if we were to consider steady, non-steady, uniform flow, would look the same as this at time 0, but at time 1, it will look different. Okay, it's not changing with respect to space, but it is changing, the flow is changing with respect to time. So non-steady, uniform flow. And then finally, non-steady, non-uniform. Would look like this at time 0, and at time 1, it would look slightly different. Okay, the velocity is changing not only with respect to space, it's also changing with respect to time. So we've defined mass flow rate. Just to remind you, mass flow rate equals rho u a. Now we can consider that, and we can consider the conservation of mass to understand fluid flowing into and out of a system. So if I was to draw a system, let's consider some sort of object, pipe flowing in, pipe flowing out, and let's draw my system boundary around that. So fluid is flowing into this system and out of the system. I'm not too concerned what's happening in the middle. So my fluid is flowing in here. This is position 1. Flowing out here. Let's call this position 2. Okay, so conservation of mass and knowing our mass flow rate, we can say the mass flow rate at position 1 equals the mass flow rate at position 2. Or rho 1 u1 a1 equals rho 2 u2 a2. Okay, so if we know some of those, we can work out what the others are. We can know the area of the inlet and the outlet. We can work out the velocity, for example. There we've got a simple system, one inlet and one outlet. We can also consider a system which would have one inlet, 2 outlets potentially, and we'd have much the same scenario. So let me draw this. So if my system boundary this time is around where these tubes split. So this is position 1. Here. Let's call this position 2. And let's call this position 3. Okay, conservation of mass again. We can say the mass flow rate at position 1 equals the mass flow rate at position 2 plus the mass flow rate at position 3. Or we could say rho 1 U1 A1 equals rho 2 U2 A2 plus rho 3 U3 A3. Now, a lot of the times, obviously, it's the same fluid, so therefore the densities would cancel. But we can use that concept to understand velocities going into and out of systems. So I've been talking about fluid flow. Now, why does fluid flow? Now, inherently, we need pressures or forces to generate that flow because there's a resistance to that flow, and that resistance comes from 2 places. There are inertial forces and viscous forces. So inertial forces and viscous forces. Now, our inertial forces associated with the mass and the acceleration of the fluid. So clearly, the fluid has a certain mass, and if we're trying to move that mass, we're going to have to use a force to move that. We know from Newton's second law, F equals ma. Force is mass times by acceleration. So if the fluid has a mass and we want to accelerate it, we're going to have to generate a force. Okay, so those are my inertial forces. We need some forces to provide some inertia to that fluid. But we also need to overcome the viscous forces within the fluid. Now, I said earlier, when we try and shear a fluid, it flows. How much it flows and how far it flows is dependent on how viscous the fluid is. The viscous forces are a measure of the resistance to shear in the fluid and are related to the interactions between the molecules in the liquid. So if we consider a wall, and let's consider some sort of fluid applying a shearing force to, so we have equal and opposite shearing force on the wall. The fluid is going to be 0 at the wall and free stream velocity away from the wall. However, how quickly that happens is going to be dependent on how viscous the fluid is. Okay, so this velocity profile I'm drawing here is going to be dependent on how viscous the fluid is. So if we think about viscosity, so if we put more viscous fluids at this end, less viscous fluids at this end, more viscous fluids, we might have a thick oil, for example. So that's to say there is quite strong forces between the molecules within the fluid, and so the interaction is quite strong, and so therefore we need to provide quite large forces to overcome those viscous forces. And then we might have water here, for example, and then maybe air right at this end, okay, where there's much smaller forces between the molecules holding those fluids together. So clearly viscosity is important, and it will describe it and will help us to understand how freely a fluid will flow. So we need some way of being able to quantify that. We need some way of being able to describe how viscous a fluid is. And we use something called the coefficient of viscosity to do that. Okay, so what do we mean by that? Well, viscosity is, like I say, talking about the resistance to shear to a fluid, shearing or resisting a shearing stress. So if we remind ourselves, shear stress or equals shear force in the shear area. And dependent on how viscous a fluid is, that will determine the velocity gradient, like I was talking about earlier, how quickly we go from that zero velocity to that free stream velocity. So our velocity gradient is clearly influenced by that viscosity. So our velocity gradient that's du by dy. So the velocity, change in velocity as y changes if y is the distance away from the wall. So our coefficient of viscosity, so once we've defined shear stress and velocity gradient, our coefficient of viscosity is simply the ratio of that shear stress to that velocity gradient. So our coefficient of viscosity coefficient of viscosity, let me spell that correctly. Coefficient of viscosity is our shear stress divided by our velocity gradient du by dy. Okay, and the units for our coefficient of viscosity, therefore, are going to be Pascal seconds. Okay, so the viscosity forces act at boundaries where the velocity gradients are high. So if we consider a pipe, fluid flowing down that pipe, so we've got some velocity here. It's going to get smaller as we get closer to the wall. So that velocity gradient is going to be dependent on the viscosity of the fluid. So if I were to draw that, if I were to draw now a line which is the front of these vectors, my velocity gradient might look something like this. Okay, where du by dy, velocity gradient, is highest at the wall. So we've talked about two different sorts of forces internally within the fluid. The inertial forces and the viscous forces. And the ratio of those will describe how the fluid will flow, whether it's laminar or whether it's turbulent. So the nature and the type of flow will be dependent on the ratio of those inertial forces to those viscous forces. And that is called Reynolds number. So Reynolds number. Reynolds number equals those inertial forces divided by those viscous forces. And Reynolds number is actually a dimensionless coefficient, and we can show that Reynolds number is equal to rho u d upon the dynamic viscosity. Okay, so rho is density, u is the velocity of the fluid, d is some dimension. It differs depending on which application you're talking about, but d is some sort of distance, some sort of length, some sort of diameter, and then we've got our dynamic viscosity on the bottom of the equation there. So if we've got a low Reynolds number, we've got high viscous forces, low inertial forces, high viscosity, low velocity, low length. So for a low Reynolds number, we would expect laminar flow. Now, very roughly, if Reynolds number is less than about 2000, we would expect the flow to be laminar. If we've got a high Reynolds number, we've got low viscous forces, high inertial forces, low viscosity, potentially high density, high velocity. So that's going to result in turbulent flow. So if our Reynolds number is less than 2000, we would expect laminar flow. Our Reynolds number was greater than 2000, we would expect turbulent flow. Clearly, that's going to change slightly dependent on the fluids and the applications. Clearly, there's going to be a transition region where we've got a mixture of laminar and turbulent flow when our Reynolds number sits somewhere between around 2000. But if it is quite low, we would expect laminar flow. And if it is quite high, we would expect turbulent flow. So what we've done today is talk about some basic concepts and basic definitions when we're dealing with fluids. There are some examples here which I will make available to you. There's 7 examples, and I want you to try those examples, looking at some of those basic definitions and basic fluid flow. Okay, so try those examples. I will make those examples available to you, solutions to those examples available to you, and we can go through those examples in class. Okay. If you have any questions or anything that we've covered there today, as always, please let me know. Get in touch. Thank you. Bye-bye.